Basically what we're talking about here is there's been some recent advances in, ironically, urban gardening and a thing called permaculture and so forth, where our standard industrial agricultural methods are being able to be compressed into very small spaces, to where the idea of having a greenhouse on Mars for a colony has gone from being something that's rather fantastical to something extremely practical on a small scale. And it's ridiculously cheap to do experiments in this area in the short term. So next slide. We're just going to define what permanent agriculture is, permaculture, briefly, how this applies to a Mars base and so forth, and then go into what I just said. So next slide. Permaculture is a contraction of permanent agriculture. It was invented in the late 50s, early 60s by a group or a person in Tasmania. And basically the idea is that you work with natural systems. You essentially build what's called a food forest, which is you have a natural system that mimics the way a forest actually works in the wild. So instead of having all straight rows, you have rows that match the contour lines of the land, and you use the borders between things instead of as barriers, you use them as opportunities because it's able to draw nutrients from one and energy from another and so forth. So it's actually a very, very clever system, but because it's built like a natural system, it requires considerably less maintenance once it gets going. So you could spend 20 hours a week getting something working for several years, but once it's working, it's maybe 4 hours a week of just grading. And this is on an Earth environment where you have things like pests and you know, various other vermin getting into your thing, which obviously you don't have that issue on Mars so much. So going on. This is a rough architecture of, it's called a 7-layer thing. You start with very low plants and then working their way up to the high plants. And then the high plants also have the benefit of climbing vines and then plants that grow in the shade better, like you know, squash and so forth. They have really large leaves, and people plant these in their garden and so forth, and they're wondering, why do you have such large leaves? Well, it's because this plant originally came from under the forest canopy where it really needed those large leaves in order to grow anything. Next slide. So what people tend to do in terrestrial applications is that they tend to rely heavily on ducks and geese and so forth, chickens, because, for example, if you have fruit fall to the ground in a standard situation, you'll eventually have a fruit fly infestation. If you have a bunch of ducks running around, they consider this to be, okay, I've got fruit and I've got protein when the maggots are in the various things. So suddenly you don't have a fruit fly infestation because there is nothing that gives you immunity to being eaten. On a similar scale, they do a lot of things where they plant plants around things that draw predators, predatory insects, so that you kill off your aphid population by planting things stuff that eat aphids like to be around, in addition to the aphids. So there's a lot of things like that that work in this environment. Again, we don't really need to worry about this on Mars. Unless we bring the pests with us, we don't really have an issue with it. So we actually get greater efficiencies than we would there. There is a group it's called the Dervaeus family in Pasadena. They actually have a 1/10 acre garden, and they are cranking out 6,000 pounds of crop on basically their yard around their house. Now in Pasadena, you have a 12-month growing season. So they actually have a little cycle, whereas in the Midwest, we tend to think of growing seasons as like this. They tend to have a growing season that does this. And they also do something that's called staggered planting, where you plant something that you plant it in the spring, and then you harvest it a few months later, and then you plant something right back in that space. You don't let it lay fallow for very long. So and by my computations, you could take something like the 2.5 floors of Mars Desert Research Station, and you could theoretically shove a garden in that big enough to support one person indefinitely. Now, if that one person actually wants to live in there, he's going to have to hang in a hammock because you've used every square inch for gardening, but it's theoretically possible. So go on. This is roughly the relationship of this whole thing. What the Dervaeus garden does is it's a combination of intensive agriculture, which is rather labor intensive, and permanent agriculture, which is less labor intensive but much more sustainable. And then in Mars agriculture, we're probably going to borrow heavily from both of these arenas. What we're not going to borrow from so much is traditional agriculture. The only thing we will really borrow from this end of things is the use of automation. The basic thing is, it used to be at the, in the year 1900, one farmer fed 4 people, and now he feeds, 100, and he's now 100 years older. Well, that's great on an industrial scale where land is not an issue, and where road is not an issue yet. But now in this environment where you have very small spaces, you don't quite have that benefit. Next slide. So how does this translate to Mars applications? Obviously, we're dealing with much smaller environments, so the very tall trees are not going to be factored into the environments. We're going to have relatively small things. Pest control obviously is not really an issue, although at the microbial level it probably will be. We'll still have to kill molds and bacteria and things like that. Aquaculture, I think, is probably a better use of things. If let's say we send an environment and we have like 3 chickens in it, and we send it to Mars, and then the astronauts arrive later and they find the 3 chickens. If they eat the 3 chickens, we will have letters from every school child in the world saying, "Why did you eat the Mars chickens?" Now, if we have tilapia or something like that have gone through 5 or 6 generations, nobody's going to be quite so freaked out about eating the Mars fish. So I think that's just a better environment all around. Also, you can do an extremely simple permaculture thing with just tilapia and duckweed. And you have a lot of benefits with that in terms of the way things work on that. And again, we can do a lot of the early experiments at a relatively cheap level. I could do it in my garage if I wanted to. Next slide. We want to switch from the other issue with a lot of the designs for a Mars greenhouse and so forth is that they tend to be very large and automated and so forth. But you're also talking about, or using hydroponics, where everything is a very finely adjusted system and very, very artificial system. In a situation like this, where things are sort of running themselves naturally, if a technology breaks down, it's a supporting technology, it's not a critical technology. It's like the difference between losing a propeller on a dirigible versus losing a propeller on an airplane. If you lose a propeller on a dirigible, it's an inconvenience. If you lose a propeller on an airplane, you've got an issue where you are not going to be in an airplane much longer. So it's kind of how we want to look at the technology here. The time demand, as I mentioned, with permaculture is a little bit more lax once you get going. Next slide. I'll get into this later. Go on, next slide. So this is my basic design. This is roughly 14 meters, top to bottom. And then we basically have a cylinder. We have essentially a light tube, which is also a cylinder hanging off the end of it. And then this gap here, and then this gigantic reflector. This is actually one of several that will be pulling light down into it. And I'll go through the rationale for this architecture one piece at a time. So next slide. That was the walkthrough. We have, as a land mass, we just sort of basically a lot of dirt on this side, and then we have a water pool here for the tilapia or whatever else we're growing, duckweed, etc. We have 5 meters of regolith above for cosmic ray protection. That's the standard for completely protecting something from cosmic ray radiation. That will stop an iron nuclei, which is the most dangerous form of cosmic radiation before it ever gets to the crew. Normally we think of that, go back. Normally we think of that in terms of, sorry, go back the way you came. You bounced. Okay. Normally we think of that in terms of protecting a crew, which has a lifespan of hopefully 80 plus years, so we really care about long-term dosage issues. Well, in a garden doesn't necessarily, we don't think of a garden as having an 80-year lifespan. Well, if you have trees in a permanent garden, they may have more than an 80-year lifespan. So you actually do have cumulative radiation issues in this case. You don't have it with like a 4-year perennial, or certainly not with the algae and so forth in the system, but you do have you still have a much more of an issue than you would if you just plant it in the spring and harvest it in the fall. The second issue, though, is that you can use this exact same structure for a crew. By being protected from the sky from every direction, if you have the next colony over the dome here, you actually get protection from the one side that is exposed. So the irony of this is, in order to get your sunlight in, you're actually facing away from the equator instead of towards it, which is how you normally do it, because all of your light is reflected in this regard. And the other thing about the light is that you need to make sure that you get a blue spectra for the early growth phases and a red-orange spectra for the phase of growth when it goes from to the flowering stage and the fruit stage for pretty much most plants. Next slide. So this is the side view. We would have, this is 20 meters right here. You could do a rather extensive food forest around essentially like almost like a miniature river, where you would force the water from one end to the other and raise whatever fish were in that environment, and then filter it on the back end for anything like, you know, the fish poop, the dead fish, whatever else, and then run it through whatever composting that you would be using for the rest of the garden and so forth. And then if you wanted to live in a structure like this, you could have a rather nice little miniature villa in that space. Just for scale, this is the size of a full-size pickup truck. Obviously not literally there, but it gives you an idea of what we're talking about. So this whole thing, while it looks vast and colonial and so forth, is really about the size of a small office building or a pole barn. It's not really that huge, and it's cylindrical, so we're basically talking about like a water tower. Not really a big deal.
It's the size of what?
It's roughly the size of a pole barn or a small office building.
Oh, barn.
Yeah, it's not that, I mean, that's a pickup truck in comparison. I mean, some of your houses are probably bigger than this.
What would you do to accommodate for the Martian winter?
We're getting there.
Okay.
Really big reflectors because you have dust storms.
But would you change the angle of the reflector?
Actually, you make an excellent point. That's why that's why it is as curved as it is. That is, I've got another slide that explains it, but it's easier to just point to it. If we can go back one slide so I can actually reach it. Yeah, here. The way this is done is this is very passive. So if it's in the spring and the fall, the sunlight would come here and come straight down. In the winter where you have a low sun, that's what this is for. In the summer with a high sun, that's what this is for. This tunnel is reflective. So it's passively gathering the light regardless of the season. And actually, if you did the same thing on the moon, this is 23.5 degrees times 2 is why this is spanned as big as it is. It's completely, because we're not tracking the sun. We don't want the mechanics of it.
So is that
we're overcoming technology with brute size.
So it's a hemispherical mirror versus a parabolic then, so it has multiple focus. It's not restricted to one spot.
Exactly. It's like one big eyeball with a big corrective lens that looks at everything. And the other thing is, when you do have dust storms, you're going to gather light from the whole sky at that point passively, so that as the light gets distributed into the sky, a solar panel still works, a concentrator doesn't. Well, you're going to need all the light you can get at that point. So the fact that you're getting passively all the sky into that zone is probably as good as you're going to do, and you're probably still going to have to subsidize it with artificial light at that point. But at least you've taken every advantage you possibly can of the environment. Okay, next slide.
Just a really quick question here. What percentage of incident light did you use to determine the size of your mirror, given that
it's not the design is not that far along yet?
Okay, but you are going to take that into account.
Yeah, we're going forward. Keep going. There's actually more to it than that, but this is.
Talking about starting with aquaculture, do you mean conventional hydroponics or?
No.
Okay,
we have 12 minutes and a lot more slides. I can't stop for questions at this point. Okay, so we already talked about that. Radiation, I pretty well walked through. Like I said, you can use that to pretty well block the sky entirely in terms of cosmic ray exposure. Next slide. Near vacuum, oh, this is another factor. The biggest window on the space station is roughly 1 meter in diameter. There's a reason for that. It has to be very thick, it has to be very precise. You don't just have gigantic glass surfaces or plexiglass surfaces when you have a near vacuum on one side and atmospheric pressure on the other side. They tend to break. So the idea here, the other reason why this is roughly igloo shaped is you want to shove that aperture down as far as possible. So this would be a matrix of smaller windows, and that's why you're trying to shove as much light through that. That whole thing may not even be exposed. It may actually be smaller than that to compensate for the fact that you don't want to blow out. Next slide. Oh, by the way, Mars gets 40% as much light as